For decades, we looked at the rust-colored deserts of Mars and assumed it was a dead, silent world. We sent orbiters and landers that took thousands of pictures, but we never had the tools to actually listen. We thought that if we ever did put ears on the red planet, all we would hear is a quiet, steady whisper of wind. That changed in February 2021. The Perseverance rover touched down carrying something no successful mission had ever deployed before: 2 highly sensitive, commercial-grade microphones. For the first time, humanity could hear another planet. The soundscape that came back through those microphones was chaotic. The timing of the recordings was scrambled, and the frequencies were physically warped compared to anything recorded on Earth. The thin Martian atmosphere acts as a physical barrier. It bends the behavior of sound waves until the familiar rules of Earth-based acoustics no longer apply. Here on Earth, acoustics follow a strict rule. All sound frequencies travel at the exact same speed. When you listen to a song, the deep bass notes and the high-pitched vocals hit your ears simultaneously, keeping the complex noise intact. Mars breaks that rule. The planet actually has 2 different speeds of sound. Low pitches move at about 537 miles per hour, but high pitches travel roughly 22 miles per hour faster. Because Mars's cold carbon dioxide is sluggish, high-pitched sound waves pass through before molecules can vibrate, gliding over them without losing speed. But low-pitched waves move slowly enough that the molecules react, bumping together. This molecular drag physically slows the low frequencies down. If you were standing on Mars listening to a distant band play, the music would reach you scrambled. You would hear the piercing notes of a flute long before you heard the heavy thump of a bass drum. Our dense, nitrogen-heavy atmosphere on Earth is an excellent carrier of kinetic energy. A normal shout can easily travel across a busy street or a wide field before fading into the background. Mars has less than 1% of Earth's atmospheric density. There simply aren't enough molecules packed together to keep a vibration moving. Because of this, sound energy dies out incredibly fast. This diagram shows the exact difference. A sound wave carrying 65 meters on Earth hits a wall at just 8 meters on Mars. Within that distance, carbon dioxide attacks high-pitched details, filtering out sharp human consonants mere feet from where they started. If 2 astronauts stood 10 feet apart and tried talking without radios, their voices would be stripped down to a distant, muffled, bass-heavy rumble. This environment also changes how we experience Martian weather. In towering dust devils, the friction of billions of dry sand grains generates massive static electricity. But this Martian lightning doesn't roar. Because the air is too thin to support explosive shock waves that create thunder on Earth, the microphones picked up a series of tiny, high-pitched snaps, the same sound as a static pop from a metal doorknob. While Perseverance listens to the surface, the InSight lander's ultra-sensitive seismic instrument was deployed to listen deep underground. It picked up a relentless, low-frequency hum. Even though Mars has no tectonic plates or crashing oceans, the atmosphere keeps the crust vibrating, constantly colliding with the deep trenches of Valles Marineris. That constant wind friction acts exactly like a bow rubbing against the strings of a violin, causing the entire planet to ring like a giant hollow bell. In 2021, the Ingenuity helicopter spun its twin rotors at 2,500 revolutions per minute to lift off in the thin air, flying roughly 80 meters away from the rover. At that distance, NASA engineers assumed the high-frequency buzzing of the rapidly spinning blades would be swallowed by the atmosphere. They expected the microphones to hear nothing at all, but the microphones picked up a clear, deep vibration. Mars had acted exactly like a natural low-pass audio filter. It stripped away the sharp, high-pitched clatter of the rotors, but it let the deep, fundamental hum of the displaced air survive the journey. This means the atmosphere acts as a physical filter, allowing deep, low-frequency vibrations to travel much further across the desert than high-pitched noise ever could. That natural filtering effect alters the sounds of our own survival technology. Tucked inside the rover is a golden box called MOXIE, a prototype factory that pulls in cold Martian air, heats it to 800 degrees Celsius, and pumps out breathable oxygen. On Earth, MOXIE's heavy mechanical compressors sound like a loud, clattering industrial machine. But when the rover's microphones recorded it on Mars, the atmosphere filtered out the sharp, metallic noises, leaving behind a smooth, rhythmic drone. Human engineering is physically distorted when amplified and filtered by the properties of an alien world. These acoustic behaviors are the atmospheric reality that future human colonists will navigate daily. They will have to account for scrambled frequencies and the constant hum of the planet beneath their boots. By recording these sounds, we moved beyond theory into the first acoustic map of an environment we once believed was unreachable.